Great. I guess you can all hear me okay. So thank you to the organizers for the invitation. And I just want to say congratulations to my grandpa Jim on your nth birthday, where n is a number between 0 and 100. Yeah, it's a standard deviation. It's got some range. So, so I'm Ken. I'm in the mechanical engineering department at MIT. These are the collaborators for the work I'm going to show you. This is David Hennon. He was my very first postdoc, and he just left me last year to become a professor at Brown. This is George Koval. He does discrete particle simulations, and I've never met him in my life. It's been a completely online correspondence, and it's actually worked very nicely. And this is my grad student, Sachit Dunatunga. And if you ask me the right questions at the end of the talk, you can see some of the cool simulations he's been doing. So let's get right to it. So what am I here for? So this is a big open question, and I want to address this question in my talk. What's the constitutive law for granular flow? OK, so that question has been asked for quite some time. Coulomb was the first to ask that question 200 years ago when he was working for the French military. And so it's a big open question, and it's been a difficult question that's looked at for a long time. But we make it slightly more tractable when we look at well-developed processes. So for now, I'm not going to study the process of transients. Okay, so the stress-strain type responses that you expect, the type of Reynolds dilation processes, shear strengthening, shear weakening. Those are all very interesting. But we still don't know how the steady process works. So why don't we try to figure that part first? Okay, so how would you predict steady flow fields? Or how would you find situations in which there won't be a steady flow field? Okay. So that's the question I want to ask. And so in order to tell you the story about this, there's been some very good recent progress on this front. And it started a while ago. But I think recently there's been some big moves on this. So on this slide, I'm going to show you one of the big steps. And this happened about 10 to 15 years ago. And this is known as the inertial granular flow rheology, or what I will call for the rest of this talk either the inertial rheology or the local law. Okay? So the good news about this rheology is a lot of it can come from a thought experiment. So let's consider this geometry here. We have planar simple shearing. All right? And in between those two rough walls, you fill it full of grains. The grains have some properties that you know about. They have a mean particle diameter d, and the density of an average grain is rho s. So let's consider the following inputs. So you apply a pressure to the top wall. And then you apply a velocity to the top wall with respect to the bottom wall, such that at steady state, you see a shear rate gamma dot. Okay? So everything that I just told you could be thought of as an input. You can control all of these things. And when you do that, you can see that there's one dimensionless number that you can make from those inputs. And it's this number here called I, the inertial number. Now, if you look at that, you'll say, oh, that's basically just the strain rate, but it's scaled by the other input parameters. Interestingly, it's scaled with the pressure in the square root of the denominator. So there's many ways to understand this in the end, but the easiest thing to say is that it's really just dimensional analysis, says that that's a relevant input variable. So then you can ask yourself the question, which what would be the dimensionless output? All right, what's the dimensionless output that I can get from that input? And what's interesting is you ask the question, what is the shear stress that is required to drive that flow, which I call tau. So how do you make that dimensionless? Well, you look at the ratio of tau to p, which is what we call the stress ratio mu. Right? Mu like friction. Okay? And the basic idea, which really springboards off of Bagnall's results from the 1950s, but was rejuvenated in some sense in the mid-2000s, was the notion that the dimensionless output mu should be a function solely of the dimensionless input I. Okay? And that's a rheology. And what's interesting is if you look in simple shear flow, planar simple shear flow, it really looks like it works pretty darn good. Okay? So here's some data of simple shear flows of particles. And you can see that there is a nice one-to-one correspondence between mu and I. So think of I like your strain rate variable. Think of mu like your stress variable. So this is a rheological curve. All right? And so what are some features of this curve? Well, there's a yield stress. All right? If you don't push with a mu value that exceeds mu s, you don't flow. But if you push harder than that, you flow faster. So this is like a Bingham rheology, except pressure shows up in a very weird way. But otherwise, it's just a Bingham rheology. And so typically, people will fit that to a straight line and say that mu as a function of I looks like mu s plus bi. So when this worked so well in simple shear, a small parade began in the granular flow community that maybe this is the answer, right? Because how did you do it in fluid mechanics? In fluid mechanics, you would do the exact same thing. You would do simple shear. You'd extract a rheology. You'd then plug that rheology into like a Navier-Stokes solver, and bam, I can now solve for flows in any geometry. Right? But the problem was they took this rheology and tried it for other geometries, and they found it only works in this one. Well, isn't that weird? It works pretty good in the other ones, but not quantitatively. So instead of showing you specific examples of where it goes wrong, because I don't have enough time, I've decided to categorize them into a few different types of effects that granular materials exhibit, but which the local rheology fails. Okay? What I think is one of the most interesting is the fact that you see grain size dependent flow fields. So whenever you have a rheology, the stress distribution determines the flow rate distribution. It's a standard rheology, right? However, what's observed in granular flows is that there is an explicit dependence as well on the grain size. There's a length scale in there. Okay? There's a cooperativity, if you will, that is completely lost from the local model. And if you don't have that cooperativity, you will not predict flow fields correctly if there is any gradient in the flow field. So your shear bands won't have the right size, et cetera. Okay? And here's another size effect that the local law cannot figure out. If I give you an inclined plane full of granular material, the local law would predict that there is one critical angle. In other words, if you ramp up to some angle theta repose, regardless of anything else, the material should flow down. However, what's observed is that if the thickness of the layer is smaller, you have to tilt higher for the material to flow down. That seems to suggest that the thickness of the layer determines also how strong the granular media is. Right? Higher layers will flow at a lower angle. Thinner layers, you have to tilt higher. Okay? That's an effect that is completely lost from the local rheology. A similar effect happens in drainage flow and governs the speed at which sand flows out of an hourglass. I don't think I have too much of time to get into this, but if you ask me questions about this, I can show you something cool. And here's a really fun one that I like a lot. This is called the secondary rheology effect, something that I lovingly refer to as motion-induced quicksand. And so here's how it works. I give you a bucket. It's full of granular material, and I stick a turntable at the bottom. If I take something with weight and I stick it on top of the granular material and just let it sit there, it'll just kind of sit there for a sec. Right? It'll sit there happily. But the moment I start rotating this turntable, which is really far away from the free surface, it suddenly turns all the sand into quicksand, and the ball bearing drops. So there it is. They start moving the turntable, and suddenly this thing is now going to sink into the sand. Okay? The local rheology would not have predicted this. The local rheology would have predicted that even if you rotated that bottom thing, it should have been able to sit there happily on the top. So let me now take you through the storyline of how we're going to build a model that I think is going to address all of those. And in order to do that, let's first get a clean diagnosis of what's going wrong with the local law. And what I really liked was when I saw this data from Koval back in 2009. So remember, the local law works really well in steady, simple shearing. So let's think of the next simplest geometry to diagnose what goes wrong. And that's this one here. So this is annular simple shearing. And what's nice about this geometry is that the strain rate is not constant in space. So you actually get gradients in the strain rate. And we can see what effect that has. So here's what Koval did in 2009. They took a bunch of simple annular cell geometries, as pictured here, and they got a bunch of steady state flows out of them using the same material. And every time that they got to steady state, they did a coarse graining over the geometry and cross-plotted mu versus I and asked, how well do I land on one single line? Because if the rheology is correct, if the local law were right, I should always land on one line. It wouldn't matter what the geometry was or what the boundary conditions were, right? And so this really stuck the nail in the coffin when I saw it. So here's what he did. This is the annular cell geometry. It has a size denoted by capital R, and it has a wall speed denoted by V wall. They run a bunch of these simulations. First set of simulations they run is they fix the wall speed, but they change how big the geometry is compared to the grain size. So every one of these data sets is a different value of R over D. And what do you observe? Well, you observe that when I is large enough, it does kind of look like all the data comes together, right? Which is what the mu of I rheology would suggest. But however, when I is very small, you can see a very clear effect of there no longer being a unique one-to-one relationship between mu and I. Like, look at all this data. And it's not noisy. It's very clear that something is really going on here, and that it's no longer true that there's a one-to-one relationship between mu and I when I is very small. Isn't that something? And note that all of these data points down here are flowing, but mu is much less than what I thought was the yield criterion, right? Mu-s was what I thought the yield criterion was according to simple shear, right? However, the same material in this geometry can now flow even when the stress is beneath that. So what's up with that, right? And then you can try the other combination. So suppose you fix the geometry, but you vary the wall speed. You try different wall speeds, and you get the steady flow. Every time you get to steady flow, you coarse grain, you scatter plot mu versus I, and you ask, how well do I fit onto the local rheology curve? And again, you see the same story. As long as you flow quickly, it looks like everything sort of lands on one line. But when you go slowly, you peel off of that single local rheology curve in a new, wacky way. Okay, so I see this and I think to myself, okay, that's a challenge. If you can come up with the right model, a simple model, that figures out this way of splitting off of the mu of I curve, you might have the answer. That was my thought. So I started to peruse the literature a little bit to try to figure out if we can come up with a rheology that might fit the bill. And I was very inspired by some of the work that had been done on emulsion flow. Okay? Emulsions. And this was the so-called KITP mechanism, which was based on this picture for how a non-local effect can work its way into a rheology. And the picture was, you imagine that plastic events, when they take place, like a rearrangement, can induce some type of fluctuations in the stress distribution away from that location, which can then help something else flow. Okay? That's a typical non-local effect, where flow here can actually help flow there. Even if at this location, the stress on its own might not be big enough for flow. It's like it's assisted by the fact that there was a flow event somewhere far away. Okay? And I like that idea, because that seemed to ring true for granular materials. And I thought it would be interesting if we could take the ideas from this picture, which had turned into their model for emulsion flow, and try to extend that to a granular material in an appropriate way to see if we can come up with a granular flow rheology with the appropriate non-locality. So here's how it looks. So if we take their ideas and we kind of try to make analogies of them, and since then we've tried to come up with better theories to explain this analogy. I'm open to your guys' interpretations if you have better ways to derive this from first principles. But let me just take you through the model here. So we invent a field called little g, the granular fluidity field. Okay, what does g do? G relates the shear rate at some location to mu at that location. So if you will, it is your relative susceptibility to undergoing flow. Mu is the load intensity. Gamma dot is how much you flow. So that's what you could think of as G. That's what G does for you, is it's an order parameter that relates those two quantities. And the notion here is that G itself obeys some dynamical PDE, which looks a lot like a Ginzburg-Landau PDE. Okay? It has something that looks like a coarse-grained energy derivative. And it looks like it has dependence on the grain size explicitly in front of a del squared term, and that would give you a non-local effect. Okay? So it's kind of like a phase field model if you're more comfortable thinking of it that way. What really caught my eye about this type of framework, though, was when you reduce this model to steady state. So right now this is still dynamical, but you can turn this into a steady state only model by doing a couple tricks from the Ginzburg-Landau book. And when you do, the system becomes like this. So let me see if I can explain to you how you would use this system. Suppose I gave you a geometry and I told you the stress field. What you could do is you would first calculate this thing, which is like a source term in a reaction diffusion like steady PDE. You would calculate this thing based on the stress field. What is G local? G local is what G would have been if the local law was right. Okay? That inertial law that doesn't work, right? Well, actually, it's just the source term here. Okay? So this is what G, the fluidity field, would have been if the local law was correct. Okay? But then what you say is actually the real fluidity field is solved implicitly from this PDE. So you have to solve this PDE and then take the answer and plug it back in up here to get the real flow field. Okay, so this PDE spreads the G field out according to some length scale. All right? When there is no length scale term because the flow is uniform, you collapse back to the local law, as you should. Right? And something else that I like about this. Suppose you're in a zone for which the local law says there should be no flow. That's a zone where mu is less than mu-s. Right? If you cancel out that term, you can still flow, actually. Look, as long as the G still solves the remaining PDE, I can now flow in a zone whose stress is actually less than µs, which is what I thought was the yield criterion. So you look at all of these things together, and it seems to suggest you might be able to use this to solve the problem. But now this was the thing that really bugged me, though, when this first came out. So you guys are physics people, right? At least most of you are. You're used to seeing length scales diverge. We've seen many talks on diverging length scales. My background is engineering and applied math, and this was the thing that I saw this, I was like, that thing is so wacky looking. I want to see for sure if it really looks like this. Okay? So what we did was we ran a bunch of DEM simulations in several different geometries. Okay? Chute flow, annular flow, shearing under gravity, and we basically extracted a plot of C versus mu. Okay? That's the length scale. How do you do that? Well, when you do DEM, you know all the contact forces, you know all the velocities. So you can construct a stress field, you can construct a velocity field, and you can look at this PDE, and actually you will know every single term in the PDE, so you can invert to find that. And then you can cross-plot it versus mu. And so every one of these data sets is what happened in different geometries. And lo and behold, it looks like this, and it blows up at µs. I couldn't believe it. It blew my mind, right? It actually works, and it's actually going on. And the black line here is the 1 over square root singularity, which was indeed what the model predicted. And so that kind of blew my mind a little bit. And what's interesting is, if you look at the remaining model, there's only one new number in this model, this new non-local model, and it's whatever the numerator is, which we denote as A, the non-local amplitude. And for these DEM disks, 0.7. Order 1, dimensionless. But with that, yeah. So those disks, you just do simple shear, and you look at where it locks up. Yeah. These are 3 different geometries. Oh, sorry, discrete element simulation. It's particle by particle. Oh, I have a software update. I'm not going to do that yet.
What is the physical meaning of µs?
µs is the yield criterion in simple shear, planar shear. Okay? But the good news is all of those we actually knew already, because those were already in the literature. There's only one number we didn't know, and it's the number we introduced when we brought in our non-local term. And we've looked at it. It looks like from this data that it's about 0.7. And so what's fun is you can then, well, I don't know if you guys care. You guys are physics people, so you're used to the diverging length scale, but this kind of blew my mind. So you guys know with a jamming diagram that as you pierce through the jamming surface, the length scale can blow up. Most of the time, people study this as a function of going down the 1 over density axis. But really what we're doing in this model is we're going down the load axis, right? Because mu is my control parameter. And when I hit µs is when everything blows up. And there have been some people who have studied that axis as well, and indeed have found a blow up as you approach µs. Lo and behold, their blow up has a scaling law of -1/2, which is what we found as well, but maybe that's a coincidence. I wouldn't look too much into that. Okay, so here it is. I propose that what's in the blue box is the steady flow constitutive relationship for granular flow. Okay, all I've done is I've made it 3D by making it tensorial. So now there's stress and there's strain rate instead of just scalars relating mu and gamma dot. But this is the definition of G. This says that I'm at the constant volume state. So all the dilation has already taken place and it stopped dilating. And this is the non-local rheology for that new state parameter G. Okay, so you put it all together and you say this model has 5 parameters total. These 2 are the local material parameters, and for most materials, those are already in the literature, so I can't make them up. So I'm just going to snag those. These are the grain parameters, and I leave those open so you can put them in as you would like. And the only really new material parameter is this non-local amplitude A. And we have calibrated for 2 simple materials. These discrete particle disks, we think it's 0.7. For glass beads, we think it's about 0.48. Okay, so here's what I do. I snap my fingers. These numbers will never change for the rest of my talk. I'm just going to show you what it predicts. So remember that dilemma that Koval showed us in the annular cell? All those different ways that mu and I split up in a real geometry. Well, if we now apply our non-local relationship with that one new variable and copy all of those boundary conditions that he had used, we see that we can actually snag every single way that mu and I split off of one curve. So again, these symbols are Koval's discrete particle simulation data. The lines are what the non-local rheology predicts. And the dotted line is what you would have predicted if you just had the local law. Okay? So you got all of this from adding that one new term with one new material parameter. And as a result of having corrected this rheological problem, the good news is we can actually now predict flows in this geometry to over 3 or 4 orders of magnitude in speed. Okay, so you can go all the way out into the tails of this distribution. This is in semi-log. And you can see that the prediction is predicting the flow field all the way out into that little creeping zone. But like I said, it's supposed to be constitutive, so it shouldn't matter what geometry you use, right? So we said, OK, take the same material with all the same parameters and stick it into new geometries. So this is flow down a rough chute. You've already seen this one. And this is flow, but with gravity present, shear with gravity. And I don't have enough time to go through every single case. But in every single case, we also varied certain geometric parameters. And these plots here show you the prediction of theory, solid lines, versus discrete particle simulation, which is the symbols. And in every case, we're able to match the data very nicely. You know, some of them a little too nicely. We thought we might have been plotting the MATLAB data twice by accident. So then we said, OK, fine. Those were discrete particle simulations. Those were 2D. Let's get some real data. Let's go to 3D. All right? So we said, hey, why don't we try to shoot big? So this is called the split-bottom couette cell. This is a geometry which previously no continuum model had ever been able to do correctly. Okay? The flow fields in this geometry really display that cooperativity effect. Okay? And so we thought, OK, might as well give it a shot. Let's see if this new model can do it. What is the split-bottom flow geometry? It looks like this. You go to Target. You buy a cake pan. You slit the bottom at some radius so that it's now 2 pieces. The inside looks like a top hat. The outside looks like a lip. You don't have to go to Target. You can go to Walmart. You fill it up. You rotate the outer piece while holding the top hat still. Okay? And it induces a very interesting looking flow profile. It looks like that when you look at the top down. Very fun to look at. And what people got interested in is what is that flow profile on the top? It looks like that. It's kind of a spread out shear band. And the reason why people got so interested in this, I believe, is because if you look at the shape of that shear band, okay, as you fill the couette cell higher and higher and higher, so this is 10 millimeters full, all the way up to 50 millimeters full, you get a very interesting looking profile for that omega function on the top. But if you focus in on just the shallow ones, where the shear band is in the middle of the flow profile, it so happens that they can all be collapsed onto one curve. And that curve is an error function. So if you ever forget what an error function looks like, you can go to Target. You can slit the body. You can fill it full of sand. You can rotate the thing. And you'll see on the top it's an error function. It is closer to an error function that you could probably draw with your hand, less than 1% everywhere to an error function. So that made people very excited because they looked at this geometry. They said, hey, it's like Heaviside on the bottom, right, where the slit is. It's error function on top. That looks like diffusion, right? But we have that Laplacian term, right? So what do we get when we try this? So I had Dave Hedden write a user element in Abacus that would implement our wacky non-local model and this geometry to see if we could predict what happens. And lo and behold, we can actually predict this extremely well. This is a prediction of theory versus experiment. Like I said, just one number, okay? And you might ask, okay, do a bunch of shallow flows. What is that shape? So we did 22 different shallow flows. And lo and behold, they all collapsed onto one curve. So this black dust that you're seeing here is a collapse of 22 flow profiles as you vary the filling height and the particle size. And the green line that's on top is an error function. So what do you know? So you get the error function with this rheology. And over here in the inset is the position of the center of the shear band as a function of how high you filled the thing up. And you can see that you get a nice match between theory and experiment with that. But perhaps more interesting than the error function gimmick is the fact that in this problem, what I think makes it really interesting is the fact that there's really 3 scales that are all connecting together. There's how high you fill the thing up. There's how big were the grains. And there's how wide was the shear band that you saw on top. Okay? So Martin van Heck did 165 experiments, okay, varying the filling height, varying the particle size. And every one of these colored data sets is colored by particle size. And we replicated all of those with our model and found that we can get this. So our model predicts all the wacky different ways in which these 3 lengths are talking to each other. And for different particle size, different filling height, it predicts the W. I guess I'm running low on time, so I can't say too much about this one. This is another case. We went to completely different geometries in 3D with glass beads. This is a 3D couette flow. And again, we took data from LoCert in 2000, and then we plotted the prediction of our model, and we got the solid line. So that's pretty good. This is data from Siavoshi and Cadroli in 2006 for dragging a plate over a bed of sand. And you get a flow field underneath the bed that looks like this. So the data is circles, and the prediction of the model is the solid line. So it looks like this thing works pretty darn good. At this point, we went back to re-verify that 1 over square root scaling law of the length scale. And we did it inversely by trying to match all of this data with different powers. And I don't have time to go into it, but the only one that works for all of them is 1/2. Okay. So in the remaining time, I'm going to try to show you a little bit about other non-local effects beyond just flow fields. So remember this quicksand effect I told you about? Where moving something far away fluidizes the material everywhere? Well, here's an example of that. So suppose you put a rod in the sand, and you apply a constant force to it. When the wall is stationary, it can't move. But wait a second, the wall starts to move, and now that rod can move. Even though if you looked at the sand flow near the position of that rod, it would look like 0. It's really far from that inner wall. And it'll keep going as long as this wall keeps moving, right? But watch what happens when the wall stops. Okay? So as long as the wall moves, the material feels like it's fluid everywhere. I wish this movie were shorter. All right? And eventually that wall's going to stop. And wall stops, rod stops. The whole time, the force on the rod never changed. So here's what they found experimentally. When the wall is stationary, there is a yield force that you need to apply to that rod to get it to move. Okay? If you're below that force, no motion. When the wall is moving, any force makes the rod move. And in fact, the formula for the velocity of the motion of that rod has a very wacky form where it's linearly dependent on the wall speed and exponentially dependent on the force. So we said, what would our model say then? Let's try this with our model to see if we can get this whole wacky phenomena of secondary rheology. We tried a simplified case where we did this in 2D rather than 3D because it would take too much time on our finite element solver. And so indeed, when the inner wall was stationary, omega was 0, on our finite element solver, we found a yield force. Okay, when you push this disk through. Okay? You had to push above a certain value to get any motion. But when the inner wall was moving, lo and behold, we find a linear relationship between the wall speed and the creep speed of the rod. Okay? Just like was shown in the experiments. And if you hold that fixed but vary the force, we find something that looks almost like a cinch. Okay? So we thought that was interesting. So you actually get this switch in behavior depending on how the wall is moving with this model. Last but not least, I want to talk about the H-stop phenomenon. Okay? So the H-stop phenomenon I told you about before was this notion that as a layer gets thinner, you have to incline the surface higher to get material to flow. Right? And it's usually shown with an H-stop phase diagram where you have H over D on one axis and angle of incline on the other axis. And you can split it into no flow and flow regimes. And this curve here is called the H-stop curve. It's the phase boundary between flowing and not flowing solutions. In other words, a flowing solution comes to a stop if you cross this curve. So we went ahead and we went back to our dynamical PDE form so that we could figure out when we would get the stopping solution versus the flowing solution. And then we compared it to the data that Pouliken had on glass beads. Remember, glass beads we have the numbers for already. And we got this. So the circles are the data for the H-stop curve from Pouliken, and the solid line is the prediction of our model. So this is a very different kind of size effect, right? This is no longer me asking, what's the flow field? This is asking, what are the conditions that are necessary for there to exist a flow field, right? And it's very interesting to see that with all the same parameters that we used to get the split bottom flows that I showed you, we can actually predict this completely different size effect. So maybe what I'll do is I will end there. I can't believe I didn't go 15 minutes over. And I'll put my conclusions up. So we have this model. It's a non-local addition to the local model, which is able to capture many of these categories of size effects that previously we couldn't get. The grain size dependence of shear features. So we were able to actually capture the flow fields in all the split bottom cells. And that's 200 plus data sets. The secondary rheology. That was the notion that motion somewhere reduces the yield criterion everywhere and enables you to flow through sand when otherwise you wouldn't be able to with a force. And the last thing was the smaller is stronger effect, where we're able to show that flows that are thinner require more stress in order to advance. What's next? Well, wouldn't it be great if you could predict the flow rate out of a silo or out of an hourglass? So that requires a bit of coding that my student is working on. If you ask me questions about that, I can show you something. But I'm out of time, so I'm going to shut up. Thanks.
If I remember correctly how the fluidity model is working, there is one more parameter that you need to solve the second order differential equation, which is the fluidity at the wall.
Right.
And this fluidity at the wall, I mean, the results are quite sensitive to that and to the assumptions that you make for that. So how do you deal with that?
Yeah, so for the boundary, you're asking what's the fluidity boundary condition? No, that's a good question. We use the simplest one that disrupts the answer the least, which is dg dn is equal to 0. We only use that because it's the easiest one to code. Now, we've also tried other boundary conditions, okay? But because of the form of that system, it's source diffusion, right? As long as you're less than about 2 particle diameters away from the wall, it looks similar. Okay? So if you have a big system, it doesn't really matter. It's only when you have a thin system that you need to be very, very, very accurate. For this last one that we did, for this is a thin system. So we didn't make up those boundary conditions. We extracted them from existing DEM simulations at the walls. We used that instead because I didn't want to go there, right? Because it could change everything in a thin system, right? Because you're absolutely right. We're working on coming up. I think Bouquet has some new predictions as to what should happen, but those were based on emulsion flows at the walls. Yeah.
You focused on numerical solutions of the constitutive law. Many of the solutions look awfully suggestive of exact analytical solutions. Have you pushed hard to find them, or are there some open, and do you think there are a lot of open problems there for all the graduate students in the room?
I would love somebody to tell me how this reduces to the error function, okay? Like it really does reduce to an error function. And I've stared at this thing, and I couldn't find a similarity solution, which you would think would have to exist. Right? I thought about trying to hire somebody to work on this, but I don't think that was enough for me to get a grant, so I didn't write it. But yeah, no, that's an open challenge to any of you who like applied math, is to try to figure out how you get this solution, because it really is dead on to an error function. There's a couple other ones in here, too, that we should consider, but I think that's the biggest one for now. We actually do have an analytical solution for this h-stop curve. So I plotted it, but I actually can write out in closed form what it is. And that's because it's a simple geometry with basically 1 degree of variation. So you could do it on paper and pencil very easily. So this one we've actually got. I actually know the function for that curve. But the other ones are tough, the ones that are really 3D flows.
Ken?
Yes?
So I would like to see your fluidity, because that's the order parameter. What does it look like in these systems?
Oh, you want to see the field?
I want to see the field.
Okay.
And in these cases, how is H related to your diverging length scale? I'm thinking if this is like a
H-stop?
size, where H-stop just becomes...
It looks almost identical to it. You are absolutely correct. So if you remember, Pouliken actually showed that the velocity correlations on the top of the, when you actually get it to flow, right? If you're above h-stop, the velocity correlations grow as you approach h-stop, right? And the way it grows is basically proportional to what I'd call C of mu. Yeah, you're right.
Ken?
Yes, Grandpa Jim.
Well, I think. Look, this square root law for the length scale. It's so simple and looks so right. There must be somebody as smart as you are ought to be able to make a theory.
No. Someone as smart as you are.
And then there were a number of things. I presume that this one, where h-stop was in fact essentially the same as that length scale, but also the rod that was sitting next to the cylinder.
Sure.
You move it away, you must be also measuring that same length scale.
Yeah, so they're all manifestations of the same non-locality, right? You have to have a length scale for any of these phenomena to happen, right?
Yeah.
Yeah, so, but the PDE, like, basically it goes down to this. If you can explain how that length scale arises in the PDE, then you would have explained how the length scale arises in all of these effects, right? So I would bring it back to one common thing, which is if you can get to the constitutive limit, if you could better understand how that thing shows up in the constitutive law, would then explain by extension how it does all of these, right? Yeah. It must be possible. I agree.
Much easier than glass physics.
Question over here. What about aging?
Excuse me?
What about aging?
Aging. Okay, well, that would be a transient effect, which we have not studied. So right now, we're only looking at either true steady flow solutions or limitations on obtaining steady flow, which is this H-stop phenomena. So when you say aging, are you referring to like what I think of as glassy aging, or the aging in a granular material where if you have creeping, I guess you would, if you have a constant stress
Creeping,
state.
dilation.
Yeah,
all
so
these effects.
let me put it this way. There are models for shear dilation. There are models for transients. There are models for strengthening over time, right? We just haven't put those in yet because we've been just trying to verify if we can get the steady solution correct. I think the more that we do this, the more confident we get that we can get the steady flow, pushes us towards adding the transients back in. Now, I'm not saying it's trivial. There's like a well-accepted single model for all the transients. But there are some simple ones we could try that would hopefully make more of like a grand model, which includes possibly aging, shear strengthening over time, those kinds of things. If you have a good one in mind, you can tell me and we can try to put it in. Yeah.
Concerning the H-stop phenomenon and
Yes.
side effect, as you know, there is also an H-start
Aha.
and side effect. So, and there is an hysteresis on that. I mean, H-start is different from H-stop.
Yes.
So is your model or rheology able to deal with this hysteresis or not?
We don't get a difference between H-start and H-stop, but that's also because the model that we're using is intended to find a limitation on a steady flow. So in other words, H-stop is when does a steady flow no longer have the ability to exist. H-start is actually a different question in some sense because it depends a lot on preparation. Right? If you look at these papers that have studied H-start, the way that the flow field progresses when you hit H-start really depends on the initial configuration of those particles. Whereas H-stop is relatively robust, right? Because it's asking, if you had a flowing layer, what would you do to be able to shut off that flow so that steady flow can't exist anymore? So my answer to you is no, we don't have H-start. Would I like to have a model which has H-start? Yeah, I would have to put bistability in here somewhere to get that. But for the time being, I have some kind of explanation for why we don't get it. The Landau theory is not quite, right? It goes up to square.
No, it's cubic.
Oh, you mean the energy is cubic.
The del G, del T.
Let me put it up. This one.
Yeah,
So you're saying that this should give me...
derivative of a cubic free energy.
Right, but if you look at this, this free energy goes from looking like this to looking like this. So we actually don't get two minima because they're both proportional to G. So you don't get what you're thinking of is, yeah, so you either have a minimum out here. So if you just look at this part alone.
The derivative of the free energy, that's zero.
Yes, so these are cubic functions, right?
So G squared and G cubed.
Yeah, so this is the energy, right? This is the energy as a function of G, right? And parameterized by mu minus mu s.
But for mu,
Because you have a double zero here. That's why. You get a double zero at the origin. So that's right. I don't have enough. You're right that a cubic generally would be able to do this, but not if the form looks like that where there's a double zero at the origin. Yeah. And as a result, you either get zero as the stable solution or flow. Yeah. Generally, you're right, but this particular one, because there's a double zero at the origin, you don't get the other one that puts two lower points in the energy function.
Nice presentation.
Thank you. I would say, but you've said that for everybody.
How about
But I wanted to say that presentation was awful. Yeah. Okay.
very nice presentation?
All right.
Can you predict the temperature effect?
If you heat it. Well, some would say, no, okay, check this out. There's an argument that says that this effect here, where the secondary rheology has a direct analogy to temperature. Okay, this is like saying that there was disturbances at the inner wall. Okay, because you rotated the wall. What does that do? Well, there's force chains. Okay, and what that's going to do is make the force chain start to fluctuate. Right? You'll see little flickers in the force chain network, even if the particles themselves aren't moving that much, which is awful lot like what a temperature would do. It puts a fluctuation in the force chain network such that a force, which previously might not have been able to push through, every now and then there's a kick in the force chain network that lets the rod go through. So there's a temperature-like analogy hidden in here somewhere. You could have also gotten this effect if you just vibrated somehow. Right? Very small amplitude vibration that you would never have been able to see, but would have shaken up the force chain network so that every now and then you would get a hop that lets the rod move through it. Does that make sense? So there's an analogy between temperature already in this case. If you wanted to add in secondary effects, like a real vibration or something, that's a good question. We haven't actually done that. But that would require coupling to yet another PDE. And it's really hard to solve this already because we have a state parameter which solves one PDE, which you plug in to solve another PDE. But if you have Abacus, you can teach it how to solve these things if you're patient. Maybe we could do it with thermal, though. Yeah.
Thank you.
Okay.
Hi, Charles.
So I guess Jim asked half of my question. So my other half is, what motivates your choice of those other quantities like G-local or the PDE itself?
Great. So G-local was not motivated at all by me. I had to steal that, right? So that was the thing that I wasn't allowed to change. G-local is the response under simple planar shear. This is what G would have been if that inertial rheology was right. And I didn't get to write that. That's other people wrote that, right? So this is the inertial rheology that I showed you on the first slide, right? This is the inertial rheology? Well, look at it this way, right? If mu is less than mu(s), G-loc says there's no fluidity. And then if mu is greater than mu(s), G-loc is this form, which if you multiply by mu should give you gamma dot according to the local law. So multiply this by mu, it cancels that off, and lo and behold, you get that gamma dot formula. Yeah.
Another way of saying it is this is valid when your length scale is tiny.
Exactly. When the length scale vanishes, this whole system goes right back to the inertial rheology. Yeah, which is like a litmus test. You would never want to write a non-local model that doesn't know how to reduce back to the local rheology in the right situation.
Okay, we have time for one last question from Matthias.
Hi, Ken.
Hi.
Matthias here. You showed a quet cell of the Losert group.
Yes.
And I was wondering if you have looked at a slight modification they have done recently. So they have put a lid on top, and they put the whole thing in microgravity.
Whoa.
So is your model capable of going that direction?
Anything that you can draw.
Let me add a challenge.
Yeah. Now that we have
it, split bottom and do the same thing, what would I find as a
Here's what I can tell you. Because it's written as a general finite element code now, you can do anything you want, we can run it, right? I mean, that's the joy of finite element method. You tell me the boundary conditions, you tell me the shape, and we can run it, right? You want to change gravity? That's easy to do on a computer with finite element specialization. Hard to do in real life unless you own a parabolic flight simulator, right? But yeah, if there's some data that has boundary conditions that we can code in, we can try it. We can see what happens. So if you send me the paper, maybe we can try it.
Qualitatively, would you find the error function for the split bottom again?
Oh, if you change gravity? If you just change gravity, absolutely. You should absolutely still find the same value because I could have just changed density instead, and that would have been like changing gravity, right? In terms of the continuum, right? It would have just changed the weight per unit volume. So I think absolutely.
Okay, so I think we have to end there, and let's thank Ken again.